We will try to solve one problem related to scattering theory. And of course, we learnt in scattering theory, we learnt about Born approximation and partial analysis. So in Born approximation, we have considered the potential is very weak. Whereas in partial analysis, irrespective of all the potentials, it will work out. And here in this problem, we are going to solve one equation, and we are going to consider that for the weak potential, both answers using Born approximation as well using partial analysis, whether they are same or not. Okay, so that's the idea. Of course, we know that Born approximation will work out only for the weak potential, whereas partial analysis will work out for all the potentials. Suppose for a weak potential in partial analysis, the result will be exactly equivalent to the result obtained in Born approximation. So that's the idea. Okay, so we are going to consider a scattering problem when del L is very small. What is del L? Del L is a phase shift. So in partial analysis, del L is very small. Prove that the expressions for scattering amplitude. So we are going to get the scattering amplitude in two methods. One is Born approximation, another one is partial analysis. They are equivalent or not. We are going to get the expressions for both Born approximation and partial analysis. They are equal or not, provided for the weak potential. So we know the scattering amplitude in partial analysis is given by this expression. So we know already this expression. Okay, here 2 e power 2I del L minus 1. Just take this expression and you just expand. So we said already that del L is very small. Del L is small. So e power x, when x is very small, e power x can be expanded. 1 plus x squared by 2 factorial, x cubed by 3 factorial goes on. So we can expand. So 1 plus x, so 1 plus 2I del L. We are going to leave the other higher terms. So here minus 1 is there, so minus 1. This minus 1 and plus 1 will go off. So you can write 2I del L alone. So instead of e power x minus 1, you can write x alone. So 2I del L. So substitute in this expression 2L plus 1 PL cos theta. This can be replaced with 2I del L. This 2I and 2A get cancelled. You have 1 by k, the remaining term. We know the expression for del L from del L, which is given by this expression. Actually speaking, we learnt this expression with sin del L. Sin del L equals this expression. And your V of R is nothing but potential. JL of KR is nothing but your Bessel function, spherical Bessel function. We learnt this expression in partial wave analysis. When del L is very small, sin del L can be written as del L. Sin theta is theta when theta is very small. So we know already. So del L can be written as exactly with this expression. You substitute. So substitute for del L. Substitute for del L. Okay. So del L is replaced with this. Is it okay? Now 2 mu k divided by h bar square k. This k and this k will cancel. You have minus 2 mu divided by h bar square. This expression. For L equal to 0, for S wave, for L equal to 0, this term will become 1. P0 cos theta, which is nothing but your 1. So this becomes 1 multiplied by 1 will give you 1. Remaining terms, minus 2 mu divided by h bar square, and this term will be your V of R. JL k of R is nothing but sin kr by r, which is a spherical Bessel function. We know already sin kr by r and r squared dr, which is nothing but your scattering amplitude. This is the expression that we got it in Born approximation. We started the expression from partial analysis. We end up with Born approximation. For the weak potential, this will work out. Is it okay? This problem is very interesting problem. Provided the case is del L should be very small. We started with the expression for scattering amplitude from partial analysis, and we substituted all the expressions for the del L. At the end, we got the expressions for scattering amplitude for the Born approximation. So we can say that for the weak potential, both the expressions are the same. Okay, either it is a Born approximation or partial wave, it is the same. Okay, so thank you students. We will start today.